Okay, Cup, welcome to Monday, July 19th. This is the 6th class of our 8 classes of summer pre-course interactive mathematics with Mathematica. Today, we're actually covering the material that's written here for last Wednesday and Friday. But once we get past today, we'll get to the notion of concave and convex function and so forth. I think we could do that all together on Wednesday. Okay, so where were we? Now, last week on Friday, we left off with simple algebraic manipulation. I haven't told you what the algebraic means, but basically we were doing a little bit of and doing matrix multiplication. We had this here. If you have x is an array. Let me make it a little bit bigger. If x is an array, okay, x vector is an array of x and say of dimension 3, okay, and a matrix is an array of a 3 by 3 matrix, right? Now let's see what they look like. Matrix form. Vector. Okay. And matrix form of a matrix. Okay, let's see what that looks like. All right, we saw that. Okay. Oop. A. Oh, sorry. I was doing something earlier. Okay, so this here is a matrix, 3 by 3 matrix, A11, A12, A13, right? This is a vector. Remember, vector is a list, an ordered list of numbers, but in mathematical notation, it's written in column form. So you have x1 on top, x2, and x3. Okay. Now, when you, by the way, let me say that in a textbook, you would, instead of seeing x bracket 1, you would normally see x subscript 1. Likewise, here you will see a subscript 1, 3. Yeah, but that's what you would see in a monograph or in a textbook. Okay, but what you notice is that here the dimension is what? Is 3 by 3, right? And this is dimension of essentially 3 by 1. And you can multiply this, and that's like taking the top row, which has 3 elements, and you take this column, which has 3 elements, you multiply them 1 by 1, a11 times x1 plus a12 times x2 plus a13 times x3, you get a number, and you put that as a product here. And then the second, you get a21 times x1, a22 times x2, a23 times x3, and you get a second number. You put it on the second row. Then you have a third number, which is a31 x1, a32 x2, a33 times x3. You get a third number. So that product will have what dimension? Well, it is 3 by 3 multiplied by 3 by 1. So the end product is going to be a 3 by 1. Okay, so this is a review of last time. So we did this this kind of multiplication. Okay, and in 2 dimension, I kind of alluded to the fact that if you have in two dimension, Okay, you can think of this as coordinate. X1 is the coordinate on the horizontal axis. X2 is the coordinate on the vertical axis. Okay, so let's start a little drawing program here. So you can think of, right? So this is X1, this is X2, right? So you have a point here, which is X1 and X2, right? X1 and X2. Now, by multiplying on the left with these four numbers, A11 times X1 plus A12 times X2, you're going to get another number, and that's going to give you a new coordinate. That's going to give you a new coordinate. Let's say it could be over here. Okay. And likewise, on the bottom row, you get another number. So that's another coordinate. So let's say it's this number here. So what happened is that because you're staying in the same dimension, right? The vector of 2 dimension lives in 2-dimension space. And you multiply it by 2, you end up with something that lives AX. Okay. You end up with something that lives in 2 dimension. Okay, again, this is one number, this is another number. So essentially, you just move to another point. Okay, so you can think of it as moving from here to here. Okay, now mathematically, well, moving makes sense if you're talking about physical dimension, right? But we're talking about mathematical object, and we can have arbitrary a definition of what the space is. It could be 10 dimension, it could be a description of something. So instead of saying we move from this point to that point, we say we transform this point to that point. And this A is the transformation. Now, technically, this A performs, write that in text, matrix multiplying, okay, multiplying, say, n by n matrix to an n-dimensional vector is equal to performing what's called linear transformation. Okay. Now, last time just now, as well as last class, I said that we are not using the word moving, we're using the word transformation. But now I'm going to add another word called linear. So it's not just any kind of transformation, it's a linear transformation. It's called linear transformation. Okay? So remember that word, we're going to define it. I'll give you another word to remember. It might be a little bit confusing, but technically, there's another word similar or related to this. It's called affine transformation. Okay? So within the same context, you see linear transformation, you might also see affine transformation. We'll talk about it as well, but I'll just give you the vocabulary right now without defining. Okay? But basically, we are going to say, okay, so you have an intuitive idea of moving from 2-dimensional point to another coordinate, another 2-dimensional coordinate, and we can generalize this to any dimension, n dimension. So you're moving a point from n-dimensional space to another point, another coordinate in n-dimensional space. We call that transformation. In particular, by multiplying by n matrix, the transformation that it achieves is restricted to this type called linear transformation. Okay, that's all it does. It doesn't do any kind of other transformation. Okay, think of transformation as some kind of processing, you know, like in food processing. If you have a knife, you can cut. If you have a hammer, you can bash maybe the steak. Okay, so different tools perform different transformation. Well, if the tool is the left multiplication by an n by n, what it does is it moves things. It moves things in a particular way, and that particular way is called linear transformation. Okay. So now I'm going to, again, talk about linearity, okay, in a sort of like an in-depth way. So it's more generalized. Well, what is a linear transformation? Well, first of all, what's the word linear derived from? Well, linearity or linear derives from the word, anybody want to guess? Line, right? Comes from the word line. Comes from the word line. Okay. If you think about it, let's draw a line. So let's say, let's clear all this. Okay. And you have some line. Just kind of make an arbitrary line. Assuming this is a straight line. Assuming this is a straight line. Okay. Now, think of it as stretching. Okay. Stretching. Let's say you have a pin here, and this is your thumb. Okay. And this is a rubber band. This is a rubber band. So this thing is fixed. This is where your thumb holds a rubber band, right? And you move your thumb around. Okay. No matter what you do, how do you transform this rubber band? Can you make it curve? No, you can't. Can you make a sine wave out of it? No, you can't. What can you do? You can only move it from here to here. Okay. Now, again, this corresponds to the notion that we did earlier. Let me draw the hand here, of moving from two-dimensional point to another two-dimensional point. But let's not focus on the point. Instead of focusing on the point, I want you to focus on the rubber band. Notice what happens to the rubber band. What it does is it changes the direction. Okay, if you think of a direction, let's say from here to there, I draw like a vector here, like an arrow. So this is what physicists are used to drawing. So focus on the rubber band and think of it as an arrow pointing from the pin to your thumb. Okay, so what happened here? Again, from here to here is multiplying by a 2x2 matrix. But I want you to focus not on what happens to the point, but what happens to the rubber band. Well, the rubber band changes the direction. It used to point here, sort of like northeast, but very far east, not very far north, to this direction, which is more like 45 degrees. Okay, so like evenly north and evenly east. Okay, so it changes the direction. But not only is it changing the direction, it's also stretching or compressing, or well, the rubber band doesn't compress, it's just sort of like a pulling in. So it just lengthens or shortens. Okay? And this is the definition of linear transformation. A linear transformation can only stretch, okay? Only stretch, meaning makes it longer, or unstretch means make it shorter in one direction, and it can also change the direction. Okay? So this is what linear transformation in an intuitive sense means. Okay, you cannot do anything else to the rubber band. If you have a piece of metal, you can curve it, you can make it into shape, into sculpture, you can do all kinds of stuff. But if all you have are, a point, a pinpoint, a pin here, a rubber band, and your thumb, the object you have is a line. And the transformation you can perform with your thumb is just stretching or unstretching, right? And changing the direction. You can change the direction 360 degrees. But those are the two things you can do. Those are the two things you can do. Yeah, those are the two things you can do. So that's the concept of a linear transformation. Now, linearity is a more general concept, but let me go on to say another concept that you need to know, which is called algebra. Okay, algebra. Now, algebra, let's go to, I'm sharing the whole screen, right? So let me go to the Wikipedia, okay? So algebra or origin of the word, okay, you will see that the word algebra came from the name of this person, this guy, okay, Al-Khawarazmi. So this is actually where the word algebra comes from. Arabic mathematician in the, I'm not sure which century, I think 13th century or something, okay? So that's him, that's this guy, this person. Oh, 9th century. Okay. So yeah, this guy was from the 9th century. So Al-Khawarizmi, you can see Al-Khawarizmi, okay? That is the origin of the word algebra. Well, anyway, so let's go back to what we mean by algebra. Okay. Now let's go to this thing. Let's go back to this. Okay. Let's clear out this picture. Well, an algebra you can think of as some kind of space or some kind of population. This is a population of animal, okay, from the same species. This is a kind of population from another species, okay. And algebra, let me write this down. Mathematical notion of algebra is like biological notion of a species. What do I mean by that? Yeah, what do I mean by that? Okay, let's say this is a Venn diagram representing two species. Okay, this is human. Okay, this is chimp. Now, human beings can interact with chimp. That's fine, it's no problem. The thing is, you can never produce a chimpanzee from human being. Okay, so if you have two people, one is Alice and one is Bob, and they get married, they produce Charlie as a boy. Okay, Alice gets married to Bob and produces a child called C, Charlie. Okay, the point is that Charlie, because Charlie is a product of Alice and Bob, both of which are human, Charlie is also a human. You can never marry two human beings and produce a child that is from another species. Okay, so you are restricted to this kind of addition within members of the same species. Likewise, you can have two chimps that reproduce, but you can never get a human being out of two chimps parents. Okay. Also, you cannot get one parent being human and another parent being a chimpanzee and married to one another and produce something else. It doesn't work. It doesn't work. Well, you can think of it as the genetic materials do not match because the genomes don't have the same dimension. It's a little bit like that. So let's just say that I have a population of, okay, let me clean all this up. Instead of a population of human being and chimpanzee, I have a population of vector here, but this one is 2-dimensional, and this one is 3-dimensional vector. Okay, if X has 2 dimensions, you can add to another 2 dimension and you get another 2 dimension. And same thing over here with 3 dimensions. But you cannot add 2-dimensional parents and get 3-dimensional children. You cannot add 3-dimensional parents to get 2-dimensional children. You cannot add one parent who has 2 dimensions and another parent who has 3 dimensions and get something else. It does not work. So this kind of operation that produces something, the operation operates on a member of a population, produces something that in turn is a population of that, is a member of that population. You can never cross species. You can never cross species. Yeah. And for this reason, if I have, okay, dimension 2 vector, okay, it's an array, say B of dimension 3, and I add it to array of C of dimension 4. Oh, sorry, technically this does not work. Yeah, it does not work. Okay, Mathematica is just going to echoes back, huh? This is what you want. You want this plus that. It doesn't work. It doesn't give you anything. Okay, because it cannot do this. It's saying you cannot add a chimpanzee to a human being and get anything. So this is just repeating back. Is this what you want? No, it doesn't work. It doesn't work. Yeah, maybe you're trying to write something. Okay, now technically this is not doable, but Mathematica, because it doesn't know what you specify, it's just going to give you echo back. But if you actually give you a real number, 1 2 3 plus 1 2, okay, oops, okay, likewise it's not doable. It's not going to give you any result. It doesn't produce anything. Now if you give you a real number that can be added together, then you can this plus this plus this plus this. Okay, so literally you can add. Now actually last week I was talking about multiplying matrix. I should also give you a notion of addition. Well, the notion of addition is very simple. Okay, if vector x is equal to 1 and 2, and y, okay, let's say x1 and x2. x1 is 1 2, and x2 is equal to 3 and 4. Okay, what do you think x1 plus x2 will be? Well, it's going to be 1 plus 3 for the first number and 2 plus 4 for the second number. 1 plus 3 gives you 6. 2 plus 4, sorry, 1 plus 3 gives you 4. 2 plus 4 gives you 6. Now, for those of you who came from SciWit, from the science track or mathematics track, you will also know that you have done this before in a math class like this. Okay, so let's just see, you have 1 and 2. So that's the point. Okay, and you have 1 2 3 4. Okay, 1 2 and then 3 4. You want to add them together. Okay, you want to add them together. The way it's done is to now replace the dot with a stick. Okay. So let's say this is a linear stick. Okay, when you add the x coordinate and y coordinate together, it's the same thing as taking the first one, leave it where it is, taking this one and move it from here to here. In other words, moving from the origin. So this is called tail to end. So this is a tail, this is a head, tail, head, tail. So you just connect the tail of the second one to the head of the first one. And whatever you end up with is the summation. So this becomes the summation. Okay. Those of you who came from a science track, you did this, it's called vector addition. And that's precisely what we just did. It's called vector addition. Okay. Now, so this is exactly what I meant earlier by saying that this is a notion of adding. So if this is a parent, Alice, and this is Bob, Alice plus Bob produces Charlie, which is the sum. And the important part is that because Alice is two-dimensional, this can be added to Bob, which is also two-dimensional. And both of them produces a Charlie, C, who is also two-dimensional. Okay. So that is this concept here. So you say something like x1 plus x2 is equal to x3 is equal to x1, x2. Okay. Now, so let me say that the notion of algebra is like biological notion of species where you can add. Okay. Now, in this case, not only can you add, what else can you do? You can also subtract. Now, it doesn't make sense with that analogy of Alice marrying Bob to produce Charlie, okay? But you imagine that just as A plus B is equal to C, you can say C minus B is equal to A, or C minus A is equal to B, right? So this is the notion, mathematical notion of algebra. Mathematical notion of algebra is like a biological notion of species, meaning you have A, you have a population, okay? In this case, you don't say population, you say space, e.g. R2 or R3, okay? Yeah, something like that. Then you have the notion that for any pair of members, A and B, Alice and Bob, okay, you have some kind of operation between binary operation. For now, I'll just put operation because operation that produces C that also belongs to that space. Okay, so when you want to define a species, you have to say there's a population of Homo sapiens. There's a biological operation called reproduction, and the result of that, okay, the act of reproduction is only valid between two members of the same species, and it produces another member of the same species. Okay, so you have population, operation, validity of operation, and the product of that operation. Likewise, I'm going to say, okay, I'm going to say that I have a space of R2, okay? Okay, so that's my real number. That's my real number, space of R2. And for any pair of number, I have an operation addition that produce C that also belongs to the same space. However, I'm more general than that, okay? Whereas two animals from the same species can only do reproduction, we have another one. We have, for any pair of products, we have another operation called subtraction. Okay. Now, not only that, this is binary operation. I also have unary operation for any number. Instead of for any member, for any pair of member, any member A, I have an operation multiply by a number. Okay, multiplying by a number can be, this number can be positive number, negative number, can be 0. Now, what happens when you multiply something by a number? If you multiply by positive 1, you leave it where it is. You do nothing to it. If you multiply by negative 1, it's like you flip. If it's over here, you flip it over here. If you multiply by positive greater than 1, you stretch. If you multiply by positive less than 1, you shrink, so or unstretch. If you multiply by negative greater than 1, you stretch and flip. If you multiply by negative but less than 1, you shrink and flip. If you multiply by 0, you make it 0, shrink down to 0. That's something you cannot do with the rubber band. But let's say this rubber band is infinitely elastic. You can stretch it to infinity. You can also shrink it down to 0. Okay, so this now we have an algebra. Okay, it's an algebra of infinitely flexible or infinitely stretchable rubber band. You can take one rubber band, stretch it, shrink it, flip it, shrink it, stretch it, shrink it. And you can also shrink it down to 0. You can take two rubber bands. Now, when you add two rubber bands, that's like saying you take one rubber band that's anchored here, stretch it here. You take another rubber band, but you make the anchor head to tail. So you move the anchor from 0, 0 to the point, and then you stretch it by the same amount. So you get that. So what we have then is operation. Again, notice, what can you do? I wanted you to think of linear as some kind of operation that you can do on rubber band. So linear algebra have two concepts, right? Linear, okay, operation, what you can do to pin down rubber band, okay? But this rubber band is infinitely stretchy, okay? Or stretchable rubber band, okay? Algebra is the notion of population and operation such that you can operate on member and produce another member. Okay. In this case, there are two types of operation. Operation that operates on one member, like stretching, okay, multiplying by a number. So, okay, linear operation is what you can do with a pin down infinitely stretchable rubber band. If you have two of them, you just move the pin from origin to the tail. Okay, so sort of like a two-step. You stretch X from 0 to the thumb. Okay, Y, you put the pin at the head of that thumb, and then you stretch it by the amount that would be Y, and then you have X plus Y or A plus B. Okay, so linear is what you can do with to pin down infinitely stretchable rubber band. Let's make it S. Okay, so you can have more than one. Algebra is the notion of a population where you have an operation and you do something that still belongs to that population. So put that together. Linear algebra is population something that you can stretch or shrink or add to or subtract one from another and produce another member. Okay. Now notice something remarkable here. When I try to give you the intuitive explanation of linear, I pointed to this kind of rubber band picture. When I try to give you an intuition of algebra, I'm talking about two things and some kind of operation. It's only when I put linear to algebra that I specify what operation that is. But once I have done it, notice I say nothing about vector. This thing doesn't have to be a vector. Okay, it can be anything that has this. Now, in mathematics, of course, we work with number, so we deal with vectors. So instead of in linear algebra in mathematics, instead of population of something, it's a population of vectors. Okay, but this can be generalized. Okay, and in mathematics, there's all kind of some funny algebra, fuzzy algebra, Lie algebra. Okay, you can even do word algebra. Okay, so let me give you an example of a word algebra. So this is linear algebra. This is an example of word algebra. Okay, let's say something like monarch. Monarch means either king or queen or queen plus female equal to queen. Right? So this is something like a word algebra. You add or subtract concept, or you say something like queen minus female plus male equal to king. Right? So this is some kind of algebra. Monarch is a human being, female human being, queen human being, human being, female human being, male human being, king human being, and you do some kind of operation. Okay, if you think of it as an operation. So this is some kind of quote unquote word algebra. Okay? And in fact, the advancement in AI in the past 5 or 10 years has been extending the power of numerical algebra to this kind of algebra, the concept algebra. So sometimes you see the word concept algebra. The concept of a monarch plus queen plus female equal to queen, or queen minus female plus male equal to king. So this is kind of like concept algebra. Okay. But now let's get back to linear algebra. So now we have this thing called linear algebra. It's a population of vector. Now, be careful, is R2, okay, R2, okay, R2. Let me ask you, is R2 and R3 same population? Is it the same population? No. Okay, you can think of R2 as space of genomes of monkeys and R3 as space of genomes of human beings. Even the dimension don't match. Now, what about this? Don't belong together. Different spaces. Okay, they don't mix. What about this? What about R2 and N2? Okay. You can think, you were saying that, oh, it's not just the size of the genome, but it's also the chemistry. Exactly. Okay. R2 and N2 also do not belong together. What's R? R is real number line. N is a natural number, so it doesn't include 1.5. It's a counting. Okay. So this would be a space. R2 would be this guy. R2 would be this guy, this space here. Okay. Whereas integer or N2 is basically the point, the grid point. Okay. Now, you certainly don't get to mix them. For example, you can get a vector that is some kind of in between here, add to it another vector that is some kind of in between here, and you get something that's in between here. So you never land on the point, or you can land on the point, right? So in this case, R2, real number, coordinate, continuous, x1, x2, and N2, which is just the integral restriction to just the grid point, they're not the same space. So a member of R2 can add together and produce something that doesn't belong to N. So really, you don't mix them. So they're different spaces. Okay. So in mathematics, you have to always define the species. Okay. Just like in biology. Okay. you're doing some kind of genetic experiment, first you have to know what species you're working with. You're working with species of R2 or species of R3. Same thing with mathematics. Now, in real life, that space, again, in real life, you don't have to just care about coordinate of just 1, 2, or 3 dimensions. This can represent a space of attributes. So what do you think defines the space? It's actually your, anybody? It's your data set. Okay, so if you have a collection of data, okay, in the form of height, weight, and inseam length, and size of your client or customer, okay, what do you have? You definitely have space of 1, 2, 3, 4. Well, actually, you wouldn't even have R2, right? Because nobody can have negative weight, negative height. So it's actually a space of positive raised to dimension 4. Okay, so that's the space of your client. Okay, it's P because it's positive. It cannot even be 0. Okay, and you have 4 of them. Now, in this operation, can you do addition? Well, just think of something like the material, the amount of cloth you need to make a dress or a shirt or whatever for your client. So you can think of addition as, you know, adding the demand. So you have 2 persons, you have more, you require more material. Okay, so something like that. So that's kind of addition. But obviously, you know, with materials, you don't need twice as much material for 2 persons. But you get what I mean. That this is some kind of general dimension. Okay, general dimension. Now you can certainly say this person, okay, let's say Alice is equal to height of 1.6 meter, a weight of 50 kilogram, an inseam of 30 inches, and waist size of 28. Yeah. And you can multiply this by a matrix or by represent weight loss matrix. Okay, then you can say new Alice is equal to matrix weight loss times old Alice. Now, because it's a weight loss matrix, it's not going to make her shorter. So you can get something like, well, she's still 1.6, right? But now she weighs a little bit less, 45. Okay, and her inseam doesn't shrink either, so it's 30. But the waist size has gone down to 26. Alice. So this. So think about it. Okay, let's go back to here. Okay, what have we got? We've got a space of something. Now, I'm always going to draw things in 2 dimensions, but you know that in physical coordinate, you live in 3 dimensions. In data coordinate, you can have 50 dimensions. Okay, so what can you do so far? You have something, Alice. You can change her direction, you can stretch her, and how's that done? How's that done? Well, the stretching is obvious, right? You just multiply by a number. So in this case, I'm going to write down what are the operations you can do. Okay. First, you can multiply by, so let's say this is x1. You can multiply by a number lambda. This lambda is a uniform stretching or shrinking. So if this is 2, you multiply x1 by 2, x2 by 2. So it's always going to be along this axis, along this line. Okay, you can only stretch or shrink. You can fit. So this is what you can do. Now, the version 1 x2 is to multiply by a matrix. It turns out that if you multiply by a matrix, you have more tools to play with. Okay? This operation, this transformation is not just about stretching or shrinking, it's about reorientation. So you can keep the same length, move it 360 degrees around, or you can do both. You can move it and shrink it or stretch it. So you can take it from here to here, to here, here. You can take it anywhere. So that is a unary operation on one thing. And the other one is binary operation. You can do two things. So x plus y equal to the sum. So there are now three things you can do. So let's look at the numerical example. Okay. So I'm going to say this is my x1 and x2. Okay. So what can I do? I can do lambda equal to 5. Okay, what can I produce? I can produce lambda x1 okay. Now let's put all this in matrix form so it looks nice. Okay, see 1 and 2 multiplied by 5 each. 5 times 1, 5 times 2 is this. Now, what if I say I want a matrix A is equal to 1, 0, and 0, 1. Instead of multiplying by lambda, I'm going to multiply by A. What do you think will happen? Well, we actually saw this. It's going to do nothing. This is a dot product, okay? It's going to do nothing. So 1, 2 becomes 1, 2. Okay, likewise, 3, 4 becomes 3, 4. It does nothing. How about this? What if I put in lambda where 1 is? Okay, if I have lambda between any kind of number, say 5, okay, and I multiply this by A, it's going to be the same thing as multiplying the whole thing by lambda. In other words, okay, this times lambda, okay, is the same thing as this times this. Now, let me write what it looks like. Matrix form. Okay. So this is multiplying, right? This is multiplying vector by a number. Now, a number, you can think of, you know, in mathematics, you're always working with number. So there's number here, there's number here, there's number here. So mathematicians think, well, we should really mean, what do we really mean by a number? Number that is kind of like a measurement to scale. So we'll call this thing scalar. So a number is a scalar. A column or list of number is a vector, okay? And a rectangular array is a matrix. So now you have three things: scalar, vector, and matrix. But what I'm writing here is to show you that you can multiply a vector by a scalar, and it just distribute 5 to 15, 5 to 20, okay? So this is going to give you something like 75 and 100. Now, on the right-hand side, you're multiplying a vector by a 2 by 2 matrix. Now, a 2 by 2 matrix, just like we said earlier, can do two things at once. It can change the direction and it can stretch or shrink. But if I take all this element to be 0, what's called, you think of it that this as diagonal line, this is kind of off diagonal element. If you make it 0 and you make the diagonal element equal to one another and you put in this number, you can see that it performs the same thing. 5 times 15 gives you 75 and nothing else. 0, nothing else. 5 times 20 is 100. So both of this will give you 75 and 100. Okay, so let me show you in proper form. Multiplying by a matrix that has no diagonal element, no off diagonal element, only diagonal element, and the diagonal element is the same thing, and that's equal to lambda. It's the same thing as doing this. It's like saying, give me a vector, and I can multiply by a matrix to stretch and change the direction. But by making this restriction that there's no off diagonal element and making the diagonal element equal to lambda, all of them, you're giving up that option to change the direction. So even though matrix multiplication allow you to move a point, transform a point by stretching, shrinking, and changing the orientation. When you do this, all you're achieving is stretching and shrinking. So it becomes the same thing. Now, technically, let me write another version of this. This is the same thing as this. 1, 1, and put lambda in front of everyone. Okay, so all this is the same thing. All this is the same thing. Take a vector, stretch it by lambda. Take a vector, multiply by a matrix that does nothing but stretching by lambda. Take a vector, multiply by a matrix that does nothing, then stretch it by lambda. So it becomes the same thing. So this is going to be equal to lambda times 15 and 20 times lambda. Same thing. So this is exactly the same thing. One is the same thing as another. Now, of course, it's a little, and so this is one operation you can do. This is a unary operation. Unary operation on vector. Okay. Now you can have what else? Oops. Binary operation on two vector. Okay. In this case, you have something like this. Okay. We did this. It's kind of easy. A, B, C, D. That's the same thing as A plus C and B plus D. Okay. You can actually have another operation called subtraction. Okay. But nobody really talks about subtraction. You know why? Because if you set lambda equal to -1, it's the same thing as this. So you're kind of combining unary operation with binary operation where you set lambda equal to -1, right? So essentially, you have just two operations. Okay. You just have one binary operation. It's called addition. Okay. If you want to subtract, you just add by a negative multiplication. Okay. So now you have two unary operations on vector and one binary operation. What are the unary operation? Multiply vector by a number. And again, because you have numbers everywhere, we're going to be specific. We call it scalar. You can multiply vector by a matrix. You can add two vectors. That's it. That's it. Okay. Now, any of you are becoming suspicious that we are missing something? Anybody? 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 Well, in high school algebra, what can you do? You can multiply, okay? You can multiply x by a number. You can multiply x by y, okay? You can also add, subtract, okay? But what else could you do in high school or in grade school that you couldn't do now? You can divide, right? Okay? You can divide. That's what you want to do. After all, if you can't divide, you can't solve something like this. 3x is equal to 18, right? So you want to do some kind of division, but this is division by a number. Okay? So let's say I do this. Okay? Let's say I do this. Okay? Now let's see if we can do equivalent of that. I can do this, right? Lambda CD is equal to right? Sorry. Okay, watch this. This is magic. You can multiply vector by scalar and get a stretching. You can reverse this totally. You can reverse this totally. How do you reverse this? How do you reverse this? Now, what you want to do is something like this. Divide by lambda. Okay? But I promise you, this is not doable. Okay? This is not doable. Okay? You want to divide. Well, it's a little bit, it looks like it's doable. So let's make it doable. Instead of this divide by lambda, which I told you is not doable. How about I multiply it by 1 over lambda? Sorry. Okay. Can I do this? Yes, I can. Yes, I can. What's the distinction? What's the distinction? Well, this is going to get you back to the original thing, right? So this accomplishes what you want. This accomplishes exactly what you want, right? You multiply or you stretch, you get this. you unstretch or shrink back by the same factor of 1 over lambda, you get the original thing back. But for some reason, I don't allow you to do this. I don't allow you to do this. Well, the reason I don't allow you to do this is because above here, I haven't specified division. Right? I haven't specified division. So it looks like I'm doing something more specialized. It's something that's more specialized. But in fact, you're doing something more general. Okay? You're doing something more general. In other words, when you divide 72 by 8 to get 9, yeah, this is a division. I'm going to make this something else. I'm not going to divide 8 into 72. I'm going to say I'm going to multiply 72 by 1 over 8. Okay, so this is exactly what we just did here. In other words, if I'm not allowed to do division, I change it into multiplication of something. That something happened to be the undoing of the first number. If you're multiplying by 8, okay, the opposite of that is to divide by 8. Now I'm going to make it more complicated. I'm going to say, if you multiply something by 8, what is the multiplication you need to do to undo what you just did? Right? So instead of multiplying by 8 and dividing by 8, you are actually going to do 2 multiplications, except the first multiplication is stretching, multiplying by 8. The second multiplication is shrinking, you multiplying by 1 over 8. And it achieves exactly what you want. Okay? So think of this as a fun game. Okay? How can you get back to the number 9, okay, without mentioning division? Okay? So you're multiplying by 8, you want to divide by 8. But for some strange reason, I forbid you to use the word division. So how do you do that? You multiply by 8. Then you multiply by something that multiplies to 8 and gets you 1. Okay? Let me write that down. This is again the notion of an overkill. But we do the overkill now because we want to generalize later. So, okay, plain text. So multiply by 8, then divide by 8 gets you back to the beginning, the original. Okay. Now, I want you to do the same thing without using the word divide. So, I multiply by 1 over 8. Gets you back to the original number. Okay. Now, I'm going to make you another sentence. I'm going to say, what is 1 over 8? 1 over 8 is something that multiply to 8 and produces 1. Okay, I'm going to insert this phrase into this. Okay. So instead of 1 by 8, I'm going to put this. Multiply by 8, then multiply by something that multiplies to 8 and produces 1 and gets you back the original number. Well, something that multiplies to 8 and produces 1 is additive inverse. Sorry, multiplicative inverse. Inverse of 8. So what I want to do is multiply by 8, then multiply by multiplicative inverse of 8 will get you back to this. So now I have replaced the word divide by 8 with the word multiply by multiplicative inverse of 8. That sounds like a lot of things to do, right? Yeah, you know how to divide by 8. But now I say, don't divide by 8. Find multiply 8 and produces 1. 1/8. Then multiply that. So, Ki Chang Chap Takatan, like I said, you know, you're overkilling this. But why do you want to overkill this? Because now I'm to matrix. So now, if I have a matrix, okay, I have something like this. A, B, C, and D, and then multiplied by, let's say, okay, x1 and x2. And this is gonna give you y1 and y2. All right? I want to do this. Equal to, okay, now look at this quickly and then erase it out of your mind because this is completely illegal. Matrix multiplied by vector gives you vector. If you want to get this vector back, you have to divide the right-hand side vector with the left-hand side matrix. But this is not doable. So I'm going to do exactly the same thing. I'm going to find something, find inverse of this. Now this inverse, just like inverse of 8 is 1/8 or 8 to the minus 1. I'm going to use the notation minus 1. This is a notation. Okay, this is a notation. This is not saying, this is not this. Okay, you could do that with 1/8. That's not a problem. You can't do this. You can't do this. Okay, so this is the more general notion. So I cannot divide by this. I'm going to find the multiplicative. Okay, now the reason I'm not going to use the word multiplicative now is because additive inverse is rather trivial, right? Just put minus sign everywhere. It's additive inverse. So for now, when I say inverse, it's multiplicative. Yeah, it's so obvious. So I'm going to use the word inverse. So find the inverse of this, and I'll call it this. And then I would multiply here. So this is everything that you will be doing in a huge class called linear algebra. Well, not everything. It's a lot. It's most of it. Most of it is this. Yeah, most of it is this. Okay. So you have grade school or high school algebra where you can say multiply, you know, something like y is equal to ax. Okay, so x is equal to y divided by a. Okay, there's no mystery. Okay, so with a simple algebra, you can multiply number by number, multiply, add two numbers, okay, and you can also divide. When you go to vector, multiplying by a number is easy. You can do that. Multiplying by a matrix, okay, is trickier, but you can still do it. Remember, equal to what? 8 times 15 plus 20 times B. And this is 15C. So right? So you can do this. The point is, once you get to this, you can't divide. So the bulk, or maybe 80–90% of what's called linear algebra class or matrix theory class is about how to find this. So matrix theory class is, let's say 80%, 80–90%, all about finding inverse of a square matrix. Yeah. By the way, a matrix doesn't have to be square, right? You saw that in your data set. Okay. So matrix theory class is all about finding the inverse. It's all about finding inverse. Okay. Now, why is this finding inverse so important to you? Why is it so important? Well, first of all, this is how you solve equation. Okay. Let me do some. Okay. Right now, we've been working with matrix and vectors and so forth. Let's go back to grade school or high school. Okay. Remember, you used to have something like 3x is equal to 9, right? So x is equal to 3. Now, you also have something called system of equation, right? You remember this? So now we are going to talk about linear algebra the same way we talk about system of equation. You used to say something like this in high school or maybe in grade school. You have n equation in n unknown. You can solve that. Or something like, what can you do? You can do 2 equations in 2 unknowns. If you have 2 unknowns, you need 2 equations. If you have 7 equations and 7 unknowns, right? You remember this? You have this kind of rule of thumb that you were always saying. You have to have the same number of equations as you have the number of unknowns. Okay, and that could look something like this. Something like ax1 plus bx2 is equal to h. Okay. Oops. Yeah. And cx1 plus bx2 is equal to k, right? So this is a number, this is a number, this is a number, number, variable, right? So how many equations do you have? 1, 2. How many unknowns do you have? 1, 2. 1, 2, right? Now, how do you solve this? In grade school or in high school or junior high, you would solve it by substitution, correct? Let's do that. Let's take the second one. x1 is equal to k, right? Minus dx2 divided by c, correct? And then you substitute in this for x1, right? And now you solve for x2. Once you get x2, you put it back here, you get x1. Everybody's happy, right? Solve for x2, substitute x2 in either equation and get x1, right? Now, can you do this with 7 equations in 7 unknown. Well, the process is more involved, right? You have to substitute x1 and then x2 and then x3 and then 4 until all the way to get to x7. Once you get x7, you substitute back to get x6, substitute both of them back, get x5, substitute all 3 of them to get x4, substitute all 4 of them to get x3, and so forth, right? So it's more convoluted, but it's always doable. It's always doable. So when your teacher would give you a problem that's always doable. My question to you is this: what if this number was 0? Okay, if this number was 0, is life more difficult? Well, it's more difficult because you can't do it this way, but certainly it's easier because you can do this. X2 is equal to k divided by d, right? And substitute that right away and get x1. So that's not a problem. That's not a problem. That's not a problem. Okay? Now, let me try something else. Let me try something else. What if this is the problem you have? Okay. And this is the original problem. And this is the second one, right? Now, this is C and this is D. I asked you this question, right? I asked you this question. What if C is equal to A and D is equal to B? Oops. Anybody? Okay, to save time, I'm not going to wait for the answer. What if C is equal to A and D is equal to B? You have this. So now, what you thought was 2 equations, the left-hand side happens to be a copy of one another. Now, what happened to your life right now? Remember, originally you solved for x1 and x2 and you're happy you get to your answer. Now, this is a situation. What happens next? Well, 2 things can happen. If k is equal to h, if k is equal to h, okay, if this were the case, then you thought you had 2 equations in 2 unknown. In fact, you have just 1 equation. So if you have 1 equation in 2 unknowns, you have infinite many solutions, right? Right? Because if this were the case, you can set x2 to be anything, right? x2 can be 1,000, okay? And x1 will be equal to h1 minus this, and the whole thing divided by a. Correct? In fact, x2 can be anything, and you get a solution. Okay? So there's infinitely many solutions. It's just a combination. So just saying that x and y has to be joined together somehow. Okay? If you give me x2, sorry, not x and y, x1 and x2. Give me x2, I'll give you x1. If you give me another x2, I'll give you another x1. Okay? So infinitely many solutions. Let's go back. What if k is not equal to h? Okay? Not equal. What happened? Now you have conflict. 2, but they are in conflict because it cannot equal to this and this at the same time. Okay, right? So the problem originally arises when A is equal to, C equal to A and B is equal to D is equal to C. In fact, this situation occurs a lot more often, right? If you see something like this and C is equal to A and D is equal to B, it's obvious. It's obvious, right? But sometimes you can also see something like this, 1.7A and then 1.7B. You would exactly get the same problem as before, because all you have to do is multiply by 1 over 1.7 here, and you get the same issue. Divide 1 here and here, you get back to the same issue. So you know that if, okay, if, let me write in shorthand. Okay, if big problem, if C and D equal to A and B. In fact, if it's equal to any kind of multiplicative number, J or D, okay, this problem, okay, this is your problem. Now, if this were the case, the problem could be two things. If x1, if y1, is also equal to b y2, then you have redundancy, right? You have then infinitely many solutions. If y1 is not b y2, then you have conflict. So no solution. Okay. So in other words, when you were saying that I have to have n equation in n unknown, okay, this is only a necessary condition for solving the system of equations. By solving, I mean get a unique value, right? It's only necessary condition. It's not sufficient condition. Okay? Because you can still have two more situations. You can have infinitely many or zero or no. So this is only about algebra, right? But this will in fact come back to you in real life. So I'm going to say right now, so this is amazing to talk about this. Right now, I'm going to say this statement. In life, you will have three possible situations. Either one, when faced with a problem, you have one and only one solution. Two, you don't have any solution. 3, you have more. In fact, you have more than one solution. In this case, you have infinitely more. Okay? Infinitely more solution. Now, this is what you had when you were in high school or grade school. This is the problem you always had. When the teacher gave you 3 equations in 3 unknown, 2 equations in 2 unknown, or maybe more difficult, 4 equations in 4 unknown, you always are guaranteed a solution because the teacher made the numbers so nice or particularly follow particular condition. So you only have this. You never run into this situation. You never run into this situation. Okay. Now, in some school, you might actually see this. Infinitely many solutions, but you never see this. Okay. So you think that this is by default how life is. If not, this is by default how life is. If not, and you never see this because in life or in grade school, you never see this. You always see this. In some school, you sometimes see this, but in practically all the school, you never see this. Okay? Because if you have a question in exam or in a class, you have to have a solution. But in life, you will have that situation, or you could have this situation. So there are 3 situations involved here. 3 situations involved here. Okay? And that situation corresponds to what we saw earlier. That situation corresponds to what we saw earlier, which is, okay, A, B, C, D are not related in any way. You have this. If C and D is some kind of multiple of A and B, you have either 2 or 3. If C and D is a multiple of A and B, and Y is also the same multiple, Y2 is the same multiple of Y1, then you have infinitely many solutions. But if C and D is some multiple of A and B, but Y2 is not that same multiple of Y1, you get a conflicting situation. You don't have any solution. Okay? You don't have any solution. Now, let me put that graphically. Okay? Okay? Let me put that graphically. When you have this equation, A x1 plus B x2 equal to y1. Okay, this is a number. Okay. All you're doing is drawing a line in x1. Okay. So if you have another equation, you have another line. And this is what I mean by unique solution. Okay. So you have 2 equations and 2 unknown. In high school, you would most of the time see this. And you will get this as the answer. You do this by substitution. The second situation is this. You have one equation that draws this line. You have another equation that draws exactly the same line. Okay. So if C is twice as big as A and D is twice as big as B and Y2 is twice as big as Y1, you get exactly the same line. So you actually don't have 2 equations. You don't have 2 lines. This is why you have infinitely many solutions, because give me x2, I'll give you x1. Give me x1, I'll give you x2. It can be anything. Another situation, when C and D is multiple of A and B, but Y2 is not the same multiple of Y1, you get conflicting. What it means is that you get parallel lines. You get no solution. Okay? So think of it as, well, how about this? Let's say you have a friend, okay? You have a friend, and a friend wants you to meet you at the intersection. Okay, I want you to meet. I want you to meet on Sukhumvit, intersect with, okay, and gives you another street. Okay, another street. A name for another street is XXX. This is the name of another street. You have three situations. One, Sukhumvit intersect with X once. Now, because this is a straight road, it can only intersect once. Two, XXX is another name for Sukhumvit. Okay, in which case that direction is useless because it just says stay on Sukhumvit. You can never meet, but at least you have a place to stay. Or three, XXX is Paramsi. Oh, Paramsi, that's not good. Phechburi Tat Nai. Phechburi. Okay, which is parallel. Right? So you don't have any solution. Right? So this is relatively simple to identify when you have just two dimensions. Okay? Linear algebra is about doing this for all arbitrary number of dimensions. Okay? You can use your eyeball, you can spot this situation. You can spot this situation. But you cannot do the same thing when it is three dimension. Let me give you an example of a three dimension. Okay, now I'm going to do this. 1, 2, and 3. Okay, now again, we don't want it to be multiple of each other. So let's say 5, 0, minus 5. Okay, 5, 0, minus 5. Now, I'm going to give you another number. Okay, so I'm going to call it, say, 3 minus 4 minus 11. Okay, that's some kind of random number. My question is, if I did this, okay, what's going to happen? Well, first of all, let's describe three situations. One situation is this. Okay, now I should have prepared some graphic for you. It's quite easy, but you know, in the interest of time, I'm going to say, well, when you draw equation, okay, with three variables, it's going to look like a plane. It's going to look like a plane. Okay. Now, if you have three equations and three unknown, you have three planes. So this plane intersect with this one on a line, and then you have another plane that intersect this here. So you have a unique solution. What else can you do? You can have infinite solution. because two of the planes are actually the same plane. It's like, two of the lines are exactly the same line. Or you can have three planes that are parallel to each other, so they never meet. They never meet, okay? So instead of drawing this, I can have two planes intersect here, and you have a third plane that's actually the same plane as the second, so you have infinitely many solutions. You can have one plane and another plane and another plane that are like Nom Chan, so they never meet, so you have no solution. How do you eyeball or how do you spot this situation? Well, the way it's done, okay, the way it's done is like this. First of all, the partition goes like this. Instead of 1, 2, and 3, okay, you have 1 or 2A or 2B. Yeah. So you separate this situation from these two situations. These two situations are problematic, and you have to go out and find out what happened. Okay. Now, to say you have one and one solution, you have to do some kind of calculation, and that calculation, okay, that calculation is, well, first of all, I should have put this in array form. 2, 3, 5, 0, minus 5, okay, and 3, and minus 4, and minus 11. This is my mysterious matrix, M equal to this. In order to determine whether or not I have the problem, I just use this function called determinant of n. And that gives you 0. So here, determinant of matrix is not 0. Okay? If the determinant of 0 then you have this problem. Now, this situation here, you have a problem because the determinant is 0. You know why it's a problem? Because instead of having 3 separate set of coefficients, I artificially create the third one by taking this one and then subtract 2 times this one. And I create this. Okay? Now, if I didn't do that, if I change it to something else, say 11.1, the determinant is not 0. Okay, it's some number. It's some number. It doesn't have to be 1. It could be some number, but it's not 0. So this is called a determinant function. Okay. So why do you have linear algebra or matrix theory? Linear, let me go back again and say what we just did today. Linear algebra, okay, you generalize notion of multiplication by a number and adding to object. So that's algebra, okay? So that's linear operation. You generalize notion of objects belonging to the same class. Okay. Yeah. So it's the same thing that you did before, but now you do this with vector. So instead of object, you have vectors. Okay. So what can you do? You can multiply by scalar. Multiplying vector by scalar. Okay, so you can do this. Okay, in the same space. So that's it. That's a notion of linear algebra. But what it allows you to solve is it allows you to solve AX is equal to B, where this is now a matrix, this is now a vector, this is also a vector. Why do you do this? Because this represents system of n equation in n unknown, but now you know how to distinguish whether this system of equation produces a unique solution. Okay. Now we're going to do quite a bit with this when you go to Chris's class, because now the mechanism of producing this. And okay, also you want to find a inverse. So A is a matrix. Matrix theory has only two components, 80–90% of it. One determines whether the system of equation AX equal to B produce a unique solution. And if it does, only if and only if it does, or if it does, then you also want to find A inverse X. You want to find A inverse so that you can solve for X is equal to X inverse B. That's it. It turns out that this here takes you the whole semester. Well, it does not have to take you the whole semester. But this is where you're heading if you're taking a linear algebra class. Now, we're doing a lot of things, but compressing a lot of material. So this will probably take you half a semester. Okay. But now, again, this is a pre-course. This is to get you up to speed so you can go to understand why you need to understand linear algebra. Okay. So ultimately, you can think of it this way. Ultimately, all along, the objective was this. If you are given n equation in n unknown, you want to know if this is solvable. If it's solvable, solve it. This is actually the two big steps that you will, again, it will require you half a semester to learn. But let me go back to when you were in grade school. AX is equal to B. Okay. When you see this in grade school, you have to, one, ask yourself whether A is equal to 0. Two, let me repeat this two-step. So now, instead of having matrix multiplied by vector equal to vector, you have 3 or A, X is equal to B, where this is all scalar. Okay. i.e. scalar equation. Okay, this is a scalar equation. Okay. Now, in a scalar equation, you have to ask yourself, determine whether or not AX produces unique solution. How do you do that? You ask yourself, you replace the whole thing, which I told you is difficult. You just ask, is A equal to 0? Okay, if A is equal to 0, then it's not solvable. If it does, if it's solvable, in other words, A is not 0, then you want to find 1 over A so that you can solve X is equal to 1 over A times B. That's it. You did this. You did this in 5th grade. You did this in 5th grade. Okay. Now, let me expand a little bit. If it's not solvable, it happens 2 things. So, yeah. If it's not solvable, okay, A not 0, then you can find A inverse. Okay. Then X is equal to A inverse B. 2A. A is 0, but so is B. Then X can be anything. Infinitely solution. Okay. And you have situation 2B. A is 0, but B is not 0. Then you have conflict, i.e. no solution. Now, once again, in grade school, you always learn about this situation. In some school, you learn about this situation, but in most school, you never learn about that situation. In life, you will always have these 3 situations. Where's the one that I said in life? In life. Okay, in life. So this is in life. Let me tell you this. In life, okay, instead of this being the most common, this being the second most common, this being the least common, this one is the most common. Okay. Now, infinite may sound like, oh, this is not impossible. You never have infinite, but you definitely have more than one solution. In life, not only is there always a way out, there usually more than one way out. Okay, and this is the basis. This is the basis of all 2A is the basis of all business decision making problems. Okay, think about it. It makes sense, right? It makes sense, right? In business situation, if you only have one and one solution, you don't have to decide. It's mandatory. You don't have a leeway. You don't make any decision because there's only one solution. If you don't have any solution, you also don't make any decision because there's no way out. In business decision making, it's based on the basis, on the premise that you always have more than one solution. And your job as business owner, analyst, or whatever, is to find the best, okay, or solution among the possible. Now, this best can be unique, or it could be just among the best. In other words, it's not the best solution, but it's up there. It's the top 10% of solution. Okay. So in real life, you want to find a good solution among the best solution. Now, to find among the best solution, the technical term for it is called optimal solution. Okay. Among the possible, they don't use the word possible, they use the word feasible. So in life, do you just have one solution? No. You don't have any solution, something's wrong. You have a set of infinitely many or more than one feasible solution. Then you have to find the optimal among the feasible. So this thing is called infeasible or infeasible. Okay? And this situation is called no problem. Well, nobody calls it that. I call it that. Okay? This situation is called no problem. Why? Because it's a problem with one solution. Once you find it, there's no problem to decide. So it's no degree of freedom or no flexibility or mandatory, right? So this is only one solution. This is unique. You don't get paid to be a business analyst to run a business if the business only has one solution. Okay. If the business solution is to make this one thing 10 units of it every single day, then you don't need business analysts, you don't need management. Okay, you just make the same thing every day. That's it, that's your solution. Okay. But in life, if you don't have any solution, then you have to be clever. So this is not a decision problem. It's more like engineering problem. And this is more like business. Okay. Now, you guys are here, you're not going to be engineer. So you're not going to run into something that's not doable and you make it doable. You're going to run into a situation where you have doable problem. But among the doable, among the feasible, there are many solutions. You have to choose the best one. So that's like something like saying, well, you have infinitely many solutions. What's that infinitely many solution? That's like being on Sukhumvit. Okay, feasible, infinitely many. Okay. Now, you don't want to just be on Sukhumvit, you want to be nearest to Lumpini Park. This is what we mean by best or optimal. And in this case, there's only one spot. There's only one place on Sukhumvit Road that's nearest to Lumpini Park. And that would be, near the intersection with the wireless with Youth Road. So this is, okay, this is given to you, infinitely many. This is business decision. You can be anywhere on Sukhumvit Road, but the criteria here is nearest to Lumpini Park. You have to find that spot. And that's your job as business analyst. Okay? So with that, I've linked the concept of system of equation to linear algebra, to matrix theory, to the concept of problem solving in real life. The last word I leave you with is this thing, this optimal thing, finding the best. And that's where we'll pick off on Wednesday. And that is also our springboard to lead into calculus. Yeah. So I have given you all the ingredients that will allow you to have the right expectation on what to do when you go to linear algebra class. Now, mechanically, how to find the solution, that's a tough one. Okay, that's a tough one. That's what you would learn in the first half of your first year mathematics. Okay, ครับ Okay, so stop sharing. So with that, I think we're done for the day, and we also run out of time. Okay,ครับ So far we've been doing quite a bit, but again, I want to link you all this. Now, traditionally, you would just learn about matrix multiplication, and matrix inverse and all of that. And then at the end, you would learn about how to apply it. But again, I want to flip this narrative. I want you to think of what you want to do first. What you want to do is find solution. What you want to do is find out whether or not system of equation is solvable. If it's solvable, where's the unique solution? Okay, and that's what matrix algebra will give you. Now, ultimately, like I said, in life, you're not paid to find out the one solution. You find out the best amongst many, and that's when you will need calculus notion. And so that will be our Wednesday class. Okay, Cap. So with that, I think we're done for today. Unless you have any question, you can stay on and ask me questions. That's no problem. But we'll stop the recording now.